Okay, I'm Sam Eisenstat. I do agent foundations at MIRI, which is sort of complicated because there is no agent foundations at MIRI anymore. We're going to begin. Yeah, so the idea behind this work, we have this idea that, if we understand the same world, do we understand it the same way? So, we might think, we all live in the world together, we all, can interact with things, so maybe we all will have this concept of the Golden Gate Bridge. We see this in practice. I mean, everyone, you can talk to people about the Golden Gate Bridge, you can show a baby who doesn't know what the Golden Gate Bridge is, and they'll realize that's a thing. And, we might think that artificial agents, if they can predict text, maybe they also know what the Golden Gate Bridge is. Maybe they have some sort of concept. And so often, I mean, yeah, this gets into a bunch of issues, but, sometimes we might have some picture that, if we have maps of the same territory, then these maps should correspond because they're of the same thing. I think things are more complicated than this. I think, we understand the same thing, we can understand the same thing in different ways in principle. But what I'm working on here is, why do we understand the same things in the same ways when we do, which is very often. And so, yeah, so what are the things we want to understand? I mean, a lot of traditional philosophy, we start with atoms and we're like, well, how are the things made of atoms? But from a kind of machine learning perspective, it's familiar that, a machine learning system, doesn't know about the Golden Gate Bridge because it knows about the atoms, and a human doesn't know about the Golden Gate Bridge because they know exactly how the atoms are arranged. And so I think it's interesting what sort of concepts we should agree on. I want to say, there's some sort of concept that we have in common that lets us talk about things. And so I'm going to propose a mathematical model of these sorts of phenomena of intersubjectivity. And so here I'm going to do a specific thing. I'm going to use probability and information theory. And so in particular, the kinds of concepts are going to be something like latent variables. And so there is, you don't need to know any of these things in particular. I'm not going to spend so much time on them. But if you have some context on some of these things, then it might give some idea of what's going on. So Dave Finetti, there's this concept of exchangeability in probability theory, where we have a joint distribution that's invariant under certain permutations of random variables. And when something is exchangeable, there's a particularly nice description of it in terms of latent variables. The roles of a die are exchangeable, and therefore it makes sense to talk about the bias of the die. Another thing, John Wentworth and David Laurel. So this actually has a lot in common mathematically with what I'm doing. It's sort of based on information theory in the same way. And so this, this describes a lot of phenomena that, where we don't have these sorts of permutations, you keep rolling the same die. And this is sort of what I want to do. And then also there's a lot of stuff in philosophy about this, or, about concepts and how, shared concepts can give the basis for, the language, a shared world. And so, the one thing that a lot of people are familiar with, the sort of Brew paradox, if, all emerald, maybe you haven't heard of that, that's fine, I'm going to move on quickly. But, should we think that all emeralds are green, or should we think that all emeralds are Grew? And so I've been talking about latent variables as sort of the model, so I'm going to say a bit about what a latent variable is. I mean, it's not, really a precise term usually, but I mean, we introduce some sort of statistical model, and there are some variables that we don't observe, but that still play some sort of role in our description of the situation. So if I have a bunch of rolls of a die, but it's not a fair die, it's a biased die, but I don't know what the bias is, one way to describe this distribution is to say, there's a probability distribution on the bias, and then each roll is a sample from the distribution on the die given the bias. And, we can do all sorts of things like this. Maybe I have some object with some three-dimensional shape, but I only see a two-dimensional image of it. So its shape is not something I can ever observe directly, but in order to talk about the joint distribution on all these variables, it makes sense to organize the distribution using the latent variables. Maybe I could describe the distribution some other way, but, there's something satisfying about describing it with these particular latent variables. And so, there's a lot of probabilistic models where we use latent variables. Again, I mean, causal models I'm going to use as examples a lot. But there's all sorts of things. You don't need to know any particular one of these, but if you have your favorite, it makes sense to try to think about this stuff as, how might this probabilistic model be described in these terms? And so structural causal models, we have some variables that have some sort of causal relations. We say how the causal relations relate to joint probabilities. And so there's a lot of special cases of this that, many special cases of this are sort of their own field of study. So hidden Markov models are something that computational mechanics people have a lot to say about. And, there's plate models. This is sort of like the De Finetti idea. I have multiple copies of the same piece of some causal model. There's factored space models. This is it's sort of like causal models. This is something that I did with Scott Garibrandt and others, and I won't say how this is different. A lot of machine learning people like sparse autoencoders. And I think interpretability is sort of, something that, a lot of people with the context of machine learning can use to think about. These sorts of problems of coming up with a shared language. I was talking about the Golden Gate Bridge. We have Golden Gate Claude. We go in there in this, big sort of black box neural net of just all these parameters, and we find a direction in the activation space that somehow has some relation to the Golden Gate Bridge. Somehow this is a natural way to describe the world, or a way to describe the world that, a bunch of agents, it just makes sense to them. They just end up doing it. And so, we don't really have a good story about why they would end up doing this a priori. It might make some sense to us. But I wanted to sort of make this, develop more of a theory for this sort of thing. And so, we don't really need another story for the rest of this to make sense about why do we care about latent variables. And so, I think this is, we can sort of say some things about why we care about latent variables that might not be so obvious if we weren't thinking about them. But, we can also say sort of that the interest is kind of established by their use in our sort of probability practices. So one thing is, it's something like analogies between probabilistic models. If we have if I have something like a causal model, if I somehow realize this causal model is wrong, I'm not sort of starting from scratch. I'm not sort of doing some sort of joint Bayesian update over the whole space of possible causal models. Somehow I can reuse parts of this causal model. I can reuse causal mechanisms. I can say maybe this causal mechanism appears in multiple places in the world. And so the latent variables sort of give a structuredness that we can use sort of to make these analogies, to make new models. This is also related to this stuff about language that, we have our different ways of understanding the world, but they all sort of have this piece that might correspond to a certain set of latent variables. And so, I mean, we can think of this, I mean, in sort of machine learning terms with like out of distribution generalization or online learning, where you can still use this sort of piece of a probabilistic model, and this is a way that this kind of analogy or generalization appears, over the course of training, more broadly in some sense, over some sort of learning process that, some agent engages in. I might have some sort of sequence of ways of understanding the world, and those might have something in common. There might be some sort of, while I've learned something has remained the same and can correspond and can form some common language between these different these different points in time. And so let's and so I'm going to start to give more mathematical detail, but what are we trying to do here, given all this setup? So I want to say we're going to introduce some latent variables to organize some model of the world, and I want to say there's some sort of objectivity to this. There's no other way of introducing latent variables that's sort of as satisfying. So I mean, really I have to, decide what the criteria are. There might be some other latent variable model that someone likes for whatever reason. Maybe it's useful to them somehow. But under some sort of conditions, I want to say some kind of uniqueness property. And so, so I'm going to talk about random variable models and latent variable models. A random variable model will be an especially simple thing. We have a probability space and some random variables. You can just think of this as a joint distribution on a set of random variables. And so this, I mean it's a definition, but it's something that, we talk about all the time. And then a latent variable model, now something is actually going to happen. But so what are the key elements of this definition? So so we're extending the space. That sort of doesn't really matter. That's part of the formalism of probability theory. But the point is we're introducing new variables. So we have these given variables, and now we also have the latent variables. So we have a joint distribution on the given variables together with the latent variables. And then sort of the thing that's going to make everything work is this contribution relation. So there is a paper. So feel free to take pictures of the slides. The slides might explain things better than the paper. But the definitions here, these are, I should say this. These are glossing over like some analytic technicalities that are in the paper. So the key thing is the relation of contribution, and so this is what's sort of different from Wentworth and Laurel. So instead of Wentworth and Laurel have like the natural latent, which is a latent variable, and I sort of want to describe a structured world with all these different parts that correspond to things that we organize the world in terms of objects and. Do you want to?
Did you just say that? What is extension?
I said we don't have to worry about that, but extension. What is it? It's a probability preserving map. It just. Okay. I'm just like restating probability preserving map in some more evocative language.
Okay, got it.
Yeah. The idea is we allow new events. So you start with. The die rolls, but we also say there's a fact of the matter about the bias. We extend the space.
You mean in omega you allow more?
Well, in lambda is an extension of omega. Like lambda sits over omega, it makes more distinction. So this is like a surjective probability preserving map. Like probability preserving is backward. It's like an event in here, the pre-image has the same mass, but the image doesn't necessarily make sense.
Yeah, and lambda is dice roll.
Yeah, like, no, omega is just the dice roll, and lambda is like the dice roll together with the bias.
Or together with the bias.
Yeah.
Oh,
Yeah, so it's like the surjection. You have the die roll and the bias, and you forget this just down to the observable space.
Omega inside of lambda is not just associated.
Uh,
Copy of omega inside lambda?
Omega, lambda surjects onto omega, so each point in omega can correspond to multiple points in lambda.
So if I just think of it one variable of the joint distribution over hidden variables and observations in the market.
Yeah, no, you're fine. This is probably too much technical detail for the slide. You just think of a joint distribution.
Black triangle?
Yeah, the black triangle. Yeah, I haven't fully explained this. So yeah, so I should do so. So the idea is we're going to distinguish. Yeah, so we're.
Sorry.
Yeah, we can.
Omega is the die rolls.
Yeah,
And lambda is the die rolls and the bias.
yeah,
Okay, got it.
yeah. See, this like makes more distinctions. It's not just like above each point in omega, which is the die roll. There's like, oh, it could have been we got this results from this bias, but it could have been we got the results from this other bias.
I see.
Yeah. So the black triangle, the contribution. So the idea is that each given variable is going to be a deterministic function of the latent variables. And so, that doesn't exactly match the story with the die roll, because it's not just a deterministic function of the bias. You have to add some extra source of randomness. It's the bias together with the idiosyncratic randomness of this particular roll. But if we do that, we can say each given variable is a deterministic function of the latent variables. But
So in the example of the die roll, what is x? Or what is could you exactly what this is?
each x sub I corresponds to a single roll of the die.
Yeah.
And then I'm going to have like y star that corresponds to the bias, and y sub I that corresponds to like the idiosyncratic randomness, the RNG you used for this particular roll.
What does Fi do?
So fi takes the latent variables and produces the given variable. So for each roll, it's a function of the bias and the, because it's not defined on lambda. It only looks at, really this is like a composition. Like, this is sort of probability notation, but it's like you have a map from, omega maps to like the space of.
This seems highly technical. Like what?
Yeah, this is too technical.
Fi, is it just projecting out?
No, it's not just. It's like I'm combining the fact of the matter about the bias and the fact of the matter about the idiosyncratic randomness in order to get what is the result of the roll.
Got it.
It was a 3. And so in particular, I didn't use all the y's. I only used the idiosyncratic randomness for the first roll. I didn't use the idiosyncratic randomness for the second roll. So each given variable is a function that's deterministic in only some of the latents, not all the latents. And that's sort of what makes this whole objectivity idea work. If we just had all the latents together all the time, it would just be like they were one big latent fact. But we want to distinguish them. We want to say, here's a bunch of different latent facts. You can distinguish them on the basis that this one contributes to these variables. This one contributes to different variables. And so, we'll see how that works. That's what a lot of the rest is like, but hopefully that's enough so that the rest makes some sense.
Is that basically set notation?
Yeah, it's like tuple builder notation, I guess. It's the tuple of yj such that j contributes to I. Yeah, no, that's right. Pi or x compose pi is equal to f compose y. Yeah. Yeah, I'm being very, I mean, it's in
If you have a measurable subscript lambda, then you project it with phi, and then apply xi to it. You get the same thing as if you you apply all the yj's that contribute to xi, apply them to this open set, and you apply fi to the pair of the tuple of the results.
yeah. And so, so in particular, I guess, this is like an example of the previous idea. So we might have, so we can turn a structural causal model into a latent variable model in this sense. And so the idea is the given variable, so you might give me a causal model in which some variables are observed and some variables are latent. And so I want to turn the observed variables into the given variables and the latent variables into the latent variables. And so, these are some, so the given variables are going to be x1, x2, x3, x4, just because, by fiat, these are the observed variables in the causal model. And then, these are the latent variables, and these arrows are, the arrows in the sense of a causal model. So y2 is causally upstream of y3. And yes, y2 is causally upstream of x3, that's right.
Is the arrow between y1 and y2 somehow represented in the latent model?
Not directly. So what we're going to do, we're going to say y1 contributes to x2 because there's a directed path from y1 to x2. But we're not going to represent this arrow as yeah. No. I'm saying this is a way to produce a latent variable. Yeah, this is an example. It's a good example to have in mind. I'm going to use a lot of examples that are causal models. Yeah.
I'd like to add a theorem tells you how deep the history of the certain of the formation and the way just to have one effect. This is also the three that the theorem was held to the digital get. You must have some model to say that. This is like
Yeah. Yeah, it's probably not too closely mathematically related because I'm looking at uniqueness and that's more like existence. Is there a tree? Probably. But it is interesting. Yeah, it makes sense. It's nice to have this. Yeah, I think I'm going to ask you to... Yeah, can you put that in Discord or something if other people want to see it also?
So in the structural causal model, you also have noise terms, right? And so if I understand correctly, noise terms also become something.
Yes, I should have said this. Yes, so these are not going to be all the latent variables. We want a noise term for each of these x's. And that's also going to, each of those noise terms is going to be a parent just of the corresponding x. Thank you. Yeah, so now we've sort of set up some ingredients, and so it sounds like we're going to give some kind of uniqueness theorem. And so how could such a uniqueness theorem work? So I'm going to have a random variable model. I'm going to have two different latent variable models. I want to say there's some kind of object that's like an approximate isomorphism between these two latent variable models. And so, we could say that zk determines yj, i.e. yj is a deterministic function of zk, and vice versa. Might be some sort of isomorphism idea. Or, we might try to make this continuous by saying it's a deterministic function, but it's like a low entropy map. The entropy of yj given zk is small. But of course, this doesn't make any sense yet, because I have the j on the left and the k on the right. It's as if I've established some sort of correspondence. I'm saying each variable determines and is determined by its partner in the other latent variable model. But how are we going to do that? We have to actually say, something like pairing them up. And so roughly speaking, what we're going to do is use the contribution relation. Two latent variables are going to correspond if they contribute to the same given variables. And so it's going to be a little more complicated than that, and we'll introduce
Latent variables in different latent variable models or within the same one?
within different latent variable models. So different latent variable models over the same given random variable model. So that, yeah. Well, we want something finer than just like taking sort of this tuple variable of everything together. But there is going to be some grouping going on that we'll see in the next slide.
So for y, lambda I, could I be thinking of two different causal models?
Yeah.
So in particular, the uniqueness, I mean, they could have completely different causal implications.
Yeah, so this is going to give some sort of constraint on like what kind of, I mean, there's going to be hypotheses. I'm not just going to say there's only one causal model for a given distribution. But if you have two models in which these hypotheses are satisfied in both of them, there's going to be something like an isomorphism. I don't know to what extent this actually gives you an isomorphism in the causal sense, like an actual, it's the same causal graph. You might need like a bit, but it should go in that direction. And I'd like to sort of continue this and say you actually do get an isomorphism of causal graphs under certain conditions. So now we're gonna have some, there's just a ton of notation, but yeah, we're going to introduce all these things with this tuple builder notation and all these symbols. And I have pictures, so you don't need to really read the symbols. I'll tell you what the pictures say. So the first one is just a shorthand. I'm going to write x subscript a for this like joint variable, this tuple, like xi for all the i's in a. And then y sub a, that's going to be what we were just talking about, this distinguishing the latent variables based on which given variables they contribute to. So
everything that is causally upstream to...
Yeah, so in this causal picture, it's going to, so if I ask you, what is y sub 1? What is y sub 1?
It's
Yeah, and this idiosyncratic guy that's not depicted. And then what is, y...
So actually, sort of the causal model misses most of the y, half of the y variables.
Well...
They have all these idiosyncratic noise things that are not depicted.
Yeah, I mean, just for the... What's it?
The noise variables are in the model, they're just not making the graph.
Yeah. And then, I guess this example doesn't let me do, like, because A is a set, right? So I can say what is y1, 2? Yeah, what yeah, plus the noise variables of x1 and x2, but not the noise variable of x3.
Right.
So that's y1, 2.
So in this picture, there are 5 y variables.
That's right.
Okay.
And so then, but I mean, YA is nice, but really I'm going to need this Y superset A and Y intersects A. So what is this? So Y superset A, I mean, really you should think of, it's everyone who contributes to everyone in A, but maybe also contributes to someone else. Oh, wait, no, sorry, I did this example, but the example was wrong. YA is the ones who contribute to everyone exactly in A. So
Why that?
So x y1, 2 is only y, and
no. Wait, sorry, the first thing you said was wrong, so I didn't hear the rest of what you said. Y12 does not include YA, because YA also contributes to X3.
just the idiosyncratic variables.
No, it's nothing, actually, because...
Why not?
It's also empty set.
Yeah, it's the constant random variable. It's like the empty tuple. Yeah, it's like, right, it's those wide...
X1 and X2 and
Yeah.
What is contribute? Oh, the contribute is defined by your system. Like,
Yeah.
But like, what should I think? If I just have the causal picture in mind, right? Should I think of something where, upon changing this, I will change all downstream variables, at least a little?
Yeah, so like YA is like if you change this, this is really like faithfulness, but like heuristically, something's in YA, if when you change it, you could change everyone in A, and you change no one outside of A.
Y123 is YA, and Y23 is YB.
Y123 is YA, Y23 is YB. Yes, that is correct. And then...
But Y1 is the noise variable on X1.
That's right. And then, so Y superset A is what we were doing, where you contribute to everyone in A, but you're allowed to also contribute to someone else.
Right, okay.
Y intersect A means you contribute to someone in A, but you're allowed to also contribute to something else. So Y so what's Y superset 1, 2, and what's Y intersect 1, 2?
Y superset 1, 2. YA, YB.
No, but also more, right?
No.
Oh, there's no, sorry,
There's
the other
no
one.
noises for 1 and 2.
No, that's...
Y intersect
Yeah,
1, 2 has YA, YB, and also the noise for 1 and 2. Y superset AB, or Y superset 1, 2 just has YA, YB.
Right, okay.
And the terminology is like clarified, like intersect, like hexagon.
Yeah. So okay. We have a theorem. This theorem is, not so great. This only applies to very special cases, but this is sort of a model for the real theorem. So what does this say? We don't. So we have two hypotheses and we have a conclusion. And so the setup, it's like we were talking about. We have a random variable model. We have these two proposed latent variable models. We want to say in what sense they're the same. So the conclusion, YA is determined by Z superset A, and ZA is determined by Y superset A.
Oh.
So it's, you aren't just determined by the corresponding guy, you're determined by it and its sort of, like ancestors. Though in some special case, you might have that no two of these are comparable, except for the idiosyncratic random variables. If you had that sort of situation, then YA just is ZA. So that's sort of a nice case where it's even simpler. But I think it is interesting. Z are the latent variables of the second latent variable model.
Can you spell out the scenario when the only correspondence is
Yeah, so I guess we don't have that here. Like if if instead I had an arrow to x1 and an arrow to x2, then it would belong to 1 and 2. And YB belongs to 2 and 3. So I'm taking out the arrow from YA to YB. So then they would be incomparable. So Y superset 1, 2 would be the same as Y1, 2, because there's no Y1, 2, 3. Right, that's this, if I'm looking at Y1, 2, I have to check, is there some Y1, 2, 3? If there's not, then it just is Y1, 2. And so I think that sort of makes it more concrete, but I think really it's pretty interesting even if YA is determined by Z superset A and ZA is determined by Y superset A. It's like you can change something in a way that depends on its parents, but you can't change it in any other way.
And determined by means there's a function.
Yeah. And so, so that's the conclusion. What are the hypotheses? So the first hypothesis is uninterestingly strong. We're going to weaken this. The first hypothesis says that Y superset a singleton is determined by Xi. So what does this mean? This means that each random variable tells you what all the latent variables that went into it are, exactly. So that's very strong. The second one is the Markov condition. If your latent variable models came from graphs, this is automatically satisfied because graphs have the Markov condition. And so, so this is the actual theorem. This is, some terrible mess. I'm going to go through some parts of it. But, there's a paper. You can read the paper. But the idea, we're making everything continuous. We're taking all this determined by and all this Markov condition, and we're going to replace it all with inequalities instead of statements. So again, I have the same sort of situation. I have two hypotheses and one conclusion. But instead of the hypotheses saying that something is zero, and then the conclusion saying something is zero, the hypotheses, it's an inequality. The hypotheses control the size of the conclusion. So, yeah. So what is? Yeah. I mean, we should just rush through this and get to more interesting stuff. But yeah. So this is saying that Y superset A is determined by. We want this to be Z superset A.
So I think it's the confusion in my head. So when you say, so the whole thing was, there was a function f that determined x given the y.
Yeah.
So being a deterministic function is not really a well-defined concept, right? Like because
So I'm saying one latent variable is almost everywhere equal to some deterministic function of some other latent variable.
the deterministic function could just be ignore everything.
Yeah, it could ignore some of them. It's free to do that.
I could just change my graph on
Yeah.
y or z in any way that I want. But you're clearly saying that even if you change the theorem still got it.
Yeah, but you're going to break the hypotheses, right? Like in the baby version, we had this backward determination. If you throw something else in, that thing might not have the backward determination. Yeah, so here we want to say that YA is determined by Z superset A. But yes, that's all it says. But yeah, instead it says Y superset A is determined by ZG. So we want to think of ZG as an approximation to Z superset A. And so, okay, let's ignore all this. Z superset A in the lattice of latent variables looks like this sort of red, it's like some upper cone, everyone above A. ZG is a bit bigger, so it's like the sort of penumbra around the upper cone. And so then this is just the Markov term. Instead of saying the Markov condition holds, I say there's some penalty based on how much it fails. But, maybe you just had a causal graph and it holds exactly. And then this is sort of the interesting one. This is saying that what makes everything work, it's going to be like this backward determination. But now the backward determination isn't going to be so strict that it's like, this is boring. So we have this sum of a bunch of terms that look like the joint entropy of Y superset A given XB, where B is going to be a bunch of sets that we do the sum over. B is going to sort of trade off with G, but yeah, we don't need to go into so much detail. So the idea is, as B gets bigger, like if I could take as my collection of B's all the singletons, I would just get back the baby theorem. But a singleton isn't going to backward determine all its ancestors.
Is this be conditional on CG or CF because G doesn't appear on the right side?
Yeah, the definition of G related it to F. But
It's the polar.
yeah, it's the polar. Yeah, this is sort of just kind of ordinary probabilistic inference. Like if I observe enough rolls of the die, I get a pretty good idea of the bias. This is like in a world where I already fixing the latent variable model, right? If we fix the latent variable model Y, if I see a bunch of these guys X, that tells me about the ones that are common parents. As the set gets bigger, the set of the common ancestors of these guys gets smaller. And also sort of the amount of information I have to reconstruct it gets bigger. So one guy can't reconstruct all its ancestors, but a bunch of guys have a better shot at reconstructing all their common ancestors. And so, in a graph like this, what are the common ancestors of x3, x4, x5? well, it's not Y3. It's not the idiosyncratic randomness of these guys. It's just Y1 and Y2. And so, you have a bunch of different pieces of information. I guess here they're not so independent because they're all mediated through Y2. So maybe this isn't such a good example. But in a lot of natural cases, we might think we can, make this sort of term small, and we get this sort of isomorphism. So yeah, that's a lot of detail. I mean, maybe someone wants to. I don't know. I mean, we're getting to the end, so I think it's interesting to say. Yeah, some more about what you can do with all this now that I've shown what some of the aspects of it are. So one thing is these kind of uniqueness of probabilistic models things, right? Like if you like causal models, often we want to do latent variable learning. We want to learn some structure, but we have to invent what the latent variables should be. And in particular, maybe there's some other way of putting the latent variables that would also produce, a good model of the observations. And so this sort of method should be able to give you these kinds of uniqueness statements that actually, in this class of probabilistic models, there is only one thing you can do. Another thing, I want this to relate to interp. This is the sort of idea that we think some sort of, hard to interpret neural network kind of model is basically doing something that makes sense to us, something that we could describe with some, some probabilistic model, maybe a causal model, in some certain domain. And so then, if it turns out that actually this is the only causal model, that gives us stronger reason to think that, maybe this is a good way of thinking about the neural net. So we can ask in particular, where are some areas where we think these conditions will be satisfied and there will be a unique causal model? Maybe there we should especially go looking to interpret things because we might have strong reason to think that what happens there will look like that causal model.
So I might have four things in this. The way I got it, the way that you match particular subsets of variables at one level, is based on whether they influence sort of the same dimension.
Yeah.
Which means if I want to say something about what part of one model corresponds to what part of another model, that really only works if the models sort of have totally different sets of latents for doing different downstream stuff that I can have. Is it correct that there's nothing in this that goes, we have here two models that have ideas about how to do stuff involving Cambridge, or maybe have 100 different variables or something, but we can't narrow it more than that. We can't say this specific prediction variable in this model for involving Cambridge corresponds to that other one. It's just all about what observable things can be influenced. Is that right?
Yeah, I maybe I don't.
I can try to restate the question.
If you think that'll help, I think
it's about if you have two latent variables that influence the same downstream variables, you want to be able to tell those apart.
Yeah, I mean, sort of the picture I have, in some complex world, there's all sorts of things going on. We might not expect two latent variables to influence exactly the same set of observable variables. Maybe we do, and then that's outside I have to take that assumption to say something. Yeah, why not just consider them one latent variable at that point?
So this does then sort of, the way which is called structure, then sort of dependent on a kind of sparsity condition.
Yeah.
How the latents influence or.
Yeah. Yeah, so in particular, a lot of stuff, uses a sort of very computational language, talks about, circuits. I'm trying to do something that's, just information. And if you do this sort of thing that's just information, you get you're not going to say there's only one circuit for some task or something. There's many ways to do a sorting algorithm or something. When you do something like this on the level of information, you have to have the hypotheses that work on the level of information. But then you get these sorts of conclusions.
So I have to admit I'm a little bit lost. There's a lot of dense information, but maybe it has to be a simplified question. So I've got a bunch of observed variables. I've got n of them, and now I'm trying to make up latent models. And as far as I can tell, this is probably wrong. What your statement is kind of, what your theorems are kind of saying is okay, so I make up some tree of, of random, latent variables that lead to this thing. And now if I use, if I make up a different tree, those are basically the same model. Is that kind of what you said?
Yeah, it's like if your trees are both...
If I make up the same tree, two different latent variable models with the same tree are basically the same model. Is that what you're saying or not?
Yeah, it's like if you make up two different trees and they're both nice and they both work, then actually you just made one tree. You made the same tree twice. Is heuristically the...
What does it mean to work? 'Cause surely I can make up a lot of different trees for any given... where is the parsimoniousness of the model?
Yeah, the parsimoniousness should be the niceness. It should be this reconstruction and Markov. The Markov is free. What's it? That's the yeah. So that's here. That's this where you can reconstruct the latents from having enough observations.
Isn't this one of your scoring functions?
Yeah. So in the paper I have these scoring functions. I left them out of the talk. They're a little complicated. The idea is we can think of this as some sort of objective function. Since we know that this produces this sort of objective world, we can look for something that has this term small and has this term small. And then so this corresponds to rho, the reconstruction score. No, H is we're just giving another name to H. It's rho is this score that's defined in terms of entropy.
Not cross entropy.
Yeah, sorry, it's not cross entropy. It's conditional entropy. Yeah, sorry. You said cross. Yeah. What's the?
It's not conditional entropy.
He has three specific scoring functions in the paper, but all of them use some kind of entropy.
Yeah, because one of them, this is one score, and then this is another score, because we care about these things both being small.
Entropy, neutral information, etc. They're not
Yeah, they're all defined in terms of information quantities.
Try again. So you've got a set of random variables. You have two different trees that both explain data well. They both have low entropy entropy. Then you're going to say those.
Well, no, it's not they predict well. We assume they both predict perfectly. But they have this backward sort of you can reconstruct if you fix the.
You have two different trees, both of which you can reconstruct the latents from the observed, and in that case, those are basically the same model. Is that how you're saying?
Yeah.
Thank you.
Yeah, we could think I should probably go to the. I can talk more about this, but I want to say that this is. This does make sense. I am putting some meaningful condition, and I want to argue that this condition is, a relatively widely interesting one.
I'm trying to understand how I think that's the case that one of the latent variables is always doing something causal like that. Not very natural. In that case, it's going to go through that, you kind of have to have a lot of entropy in the idiosyncratic random variables.
Not the idiosyncratic. It's you're going to have a bunch of big ones that influence a lot of things that are hard to disentangle from each other. I don't know. Is that okay? Yeah, maybe. I want to get to some other points, and I don't have much time. So I think it's a good question. I think this is the sort of thing I'm interested in developing further.
Yeah.
And yeah, we're out of. Are we? I was told 5 minutes 1 minute ago. The other talk is discussion. The other talk is supposed to follow this. I don't know.
Well, Fernando.
Yeah. Yeah. I do want to wrap up and let people. But I want to get to some ending points because I think they're. Yeah. Of course you can leave if you want. There's going to be discussion soon. I like the points I make at the end, so I would like if you stayed another like 5 minutes, but you're free to leave.
Starting literally now, so
Yeah. 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 Okay. I'm gonna rush through the rest of the talk. So.
We can start the next session with the main points that you want to make at the end.
I think we
I think I should just. Okay. Yeah. So the. Yes, I'm talking about all these like probabilistic models that we use in machine learning, statistics, whatever. But also like there are all these cool distributions that we get from physics. We have an Ising model or whatever. We have things with wave packets, with solitons, with things that we think of as some sort of high-level emergent object. And so it really feels like that should be a latent. And so I want to figure out if that can be latent. And so, more broadly, sorry, I want to just rush through these points and then have questions. Yeah, so more broadly, I want us to think about, epistemology, machine learning, whatever, in a way that more connects to meaning, in a way that more connects to, like, we do what we do that involves thinking of the world as having some stuff there, and we're trying to understand this stuff. I mean, I want to have like a learning theory of representation. I mean, what the LLM labs do with the models. They're trained on predictive objectives, but the point of them is not actually to be predictive. The point of them is to, well, I mean, you can say, to do things for us, but there's something that intermediates. We tell them we want them to predict. Really, we want them to do something else. But somewhere in the middle, there's some sort of understanding. We want to think about models. Do they understand the world? What do they understand about the world? And so, traditionally, the language we get from CS theory to talk about this stuff is sort of learning theory, generalization. Does this get a good performance on the test set? But really, I want to talk about representation. Does this form the right representations? If you do this sort of, out of distribution or online sort of setting, do you have the representations that make this make sense? And so I want to take this stuff and make it more have learning theory in it. But also, I want us to generally be more honest about what machine learning is actually doing. We know how to say, is it generalizing? But what we want to say is it forming the right representations? Let's use this language of representations, of meaning, of language, of first-order logic, in talking about what models are doing. And I want these sort of theoretical ideas to provide sort of a basis for this. And then, more broadly, I think this relates to, how do we want to interact with artificial agents? How do we want to express our values? We often express our values in terms of the things that we find out there in the world. We say, I care about how other people feel. I think of them as having some mental states. And, what we're really asking for is something that, maybe is hard to state, even in terms of these sort of concepts that emerge from us trying to understand the world. But we're at least getting closer when we talk not in terms of like, oh, does it get a good score on this, on this training set we came up with, on this RL environment we came up with. What we really want is, does it understand the things that we understand as being in the world? What can we say in that language? And so that's what I hope this will, be able to lead to. That's sort of the directions I want to develop it in. The directions I want it to be able to interact with. And so, now you're all free to go and free to ask me questions. And yeah, I mean, maybe this should just be Fernando's session now. Yeah, no more questions. If you want to ask me a question, it's part of Fernando's session.